Any kind of testing is always a matter of controlling the device that is being tested and observing its behavior. In the case of an SoC, we can only control the chip through the input pins and observe it through the output pins. We cannot directly access internal nodes to control or observe their states. For each fault, we need to manipulate the inputs to establish a circuit state that is both sensitive to the presence of the fault and will propagate the response to an observation point. Sensitive to the fault means that the circuit will produce different responses depending on whether the fault is present or not. We then compare the observed response to the predicted value. In this given example, the AND gate's output is stuck at 0. To observe this effect, both inputs should be at logic 1 of the AND gate, and to make that condition we need output of both the combinational block should be 1. To make this happen, we will have to control the flops to get the required value at the input of the combinational blocks. This is how the test is problem of control and observation. For a modern chip, there are millions and millions of faults, so it can take a long time to compute all these tests, and can produce a very high volume of data, and take a long time to apply. Over the years, many simplifications have been adopted to reduce computation time, test data volume, and test time in manufacturing, and we will look at a few of these cases. Most, however, are buried deeply in computational algorithms, and do not change the basics of test generation, so we will ignore them. If you are already familiar with test and concepts such as scan, some of these slides may be review. We are going to be starting from the beginning, with functional test patterns. This is the basic structural automatic test pattern generation, ATPG, loop. A single fault is randomly selected from the consolidated fault model. The test generator attempts to generate a test for that fault. If unsuccessful, the fault is marked as untestable, and another fault is selected. If a pattern is successfully generated, it is passed to the compaction program. This program merges tests that are compatible, same clocking sequences, which we have not introduced yet, and no conflicting values on any input, into single patterns. Eventually, the compaction program determines that some set of patterns is as full as they are going to get, and passes them to the fault simulation program. The unspecified bits of each pattern are filled, usually with random data, and then the netlist is fault simulated with this pattern. First, the pattern is simulated with no faults applied to the netlist, and the results are recorded. Then the netlist is resimulated with each undetected fault, one at a time. The result of each of the simulations is compared to the results with no faults, and if there is a difference, that fault is marked as detected. Finally, the pattern is appended to the set of simulated test vectors if it detected at least one fault. Committing experiments is a way of saving the patterns, faults tested by patterns. The patterns are saved in the test mode. Experiment name is no longer valid. The faults tested by the experiment are marked as tested. To all additional experiments in the test mode would start off at given test coverage level. If cross-test mode mark off is turned on, then other test modes would also have these faults as tested. The commit experiment updates the global fault list to mark as detected fault if any faults detected in the design. All test generation runs are made as uncommitted tests in a test mode. Experiment commit moves the uncommitted experiment test results into the committed vectors test data. Marks faults as tested are updated in the global status. Once the experiment is done, patterns are saved in test mode data, and experiment removes. In diagram below, we can see, if experiment A is run first and committed, experiment B will start with a detected coverage that includes experiment A.